Hi everyone. We're continuing with Chapter 5. We're now in Section 5.6 and we're talking about rational functions. So we've touched on rational functions back in Chapter 3 when we were introduced to functions. We're going to go deeper in this section. In this section, students will use arrow notation, solve applied problems involving rational functions, find the domains of rational functions, identify vertical asymptotes, identify horizontal asymptotes, and graph rational functions. So here is an illustration of a rational function. This is actually a rational function that you've seen before. This was in our toolbox, f of x equals 1 over x. And what happens is there are asymptotes. These are lines we don't see, vertical and horizontal, where the graph doesn't cross that vertical or horizontal line. So the graph approaches it, but it never actually crosses it. And so to describe this behavior, we use arrow notation, which you have seen before, but this takes it again a little bit deeper. So if you're looking at this graph, you'll see that the end behaviors are written in these 4 places. So if you'll look, this is the x-axis. This is as x is approaching infinity. Here's x is approaching negative infinity. So what we want to show is what is going on with the graph. What is it approaching in terms of the y, or the f of x? So in this case, as x is approaching negative infinity, it looks like the graph is approaching 0. So it's kind of like this is a ceiling right here. This graph is never going to go past it on this side. Now, if we're going the other way, if you are approaching the graph from the left, the y looks like it's going down. Now, what's happening on the x? It is approaching this vertical asymptote of 0. So as x is approaching 0 from the left, so notice what they do here to show that we're approaching 0 from the left, because you can approach it from the left or from the right. So when they're saying we're approaching it from the left, they put a little negative sign here with it. So as x is approaching 0 from the left, the graph is going down to negative infinity. On the right-hand side, we see 2 behaviors. As x is approaching 0 from the right, so notice they put 0 plus, the f of x is going to infinity. And as x is approaching infinity, what's happening to the graph? It's getting closer and closer to this 0, and it's never going to cross it. So here is a list of the different symbols. Instead of a number for the asymptote, they use a. So as x is approaching a from the left, this is x is approaching a from the right. You've seen the rest of these before. X approaching infinity and negative infinity, f of x approaching infinity and negative infinity, and then there's just f of x approaching a. Alright, so here we have the actual definition of a vertical asymptote and horizontal asymptote. A vertical asymptote of a graph is a vertical line x equals a, where the graph tends towards positive or negative infinity as the inputs approach a. So as the input, or the x, is approaching a, in this case it's 0, then the graph is either approaching negative infinity or positive infinity. That's what's happening there. So the graph will never cross a vertical asymptote. So a horizontal asymptote of the graph is a horizontal line y equals b. They have it here, y equals 0, where the graph approaches the line as the inputs increase or decrease without bound. So as the input is increasing, as x is increasing, the f of x is approaching this line here, y equals b. As x is approaching negative infinity, it's going this direction, then the graph is approaching the horizontal asymptote, y equals 0 in this case. Okay, so let's look at an example. It says, sketch a graph of a reciprocal function shifted down 1 unit and left 3 units. Determine the horizontal and vertical asymptotes. So normally we have asymptotes at y equals 0 and x equals 0. So starting at the origin, if we shift down 1, so we're going to go down 1 and left 3. Okay, so down 1 and left 3. Then we have a vertical asymptote at x equals -3 because we shifted left -3. And then we have a horizontal asymptote. We shifted down 1 unit. So we have a horizontal asymptote right here. Now, if you will go back and look at the shape up here, you can see that from the asymptotes, if you go right 1 and up 1, you'll have a point. Left 1 and down 1, you'll have a point. So let's do that. From the asymptote, if I go right 1 and up 1, there's a point. Left 1 and down 1, there's a point. And then if you'll look at the graph, you can kind of see that there's a point about halfway there between 0, 1, 1, up 2, but between 0 and 1 for the x, and then between 1 and 2 for the x, you go up about a half as well. So I'm thinking there'll be a point here and one here. This will curve. It will approach the asymptotes but never cross. Same thing is going to happen in this direction. Alright, so you try it. Try to sketch the rational graph. Okay, it's just a sketch. This time you're going to find the horizontal and vertical asymptotes of the reciprocal squared function that has been shifted right 3 and down 4. So pause the video, and when you'll come back, we'll go over it. Okay, so if we shift right 3, 1, 2, 3, we'll have an asymptote here at x equals 3. And then if we go down 4, 1, 2, 3, 4, we have a horizontal asymptote at y equals -4. And if you will recall what happens on this particular graph, this is a transformation of 1 over x squared. And it's going to look something like this. And as you're doing these, if you're not quite sure what something looks like, you can always go to Desmos. 1 over x squared. That's the basic shape of the graph, and you can use that to help you sketch the shape. So here we're going to actually define a rational function is a function that can be written as the quotient of two polynomial functions p of x and q of x. So I've got a rational function on top, a rational function on the bottom. You can see that the rational function has two polynomial functions, which is what this represents here. Q of x obviously can't equal 0, otherwise it would be undefined. Here's an example of what the graph looks like, but we've already graphed a couple of these, so we're just going to scroll down to the next item on the list, which is finding domain. So for domain, this should actually just be a review. We're going to set the denominator equal to 0, because we know that where the denominator is equal to 0, that's where the graph is going to be undefined. So we're going to solve to find the x values that cause the denominator to be equal to 0, and then the domain is all real numbers except for those found in step 2. So for this one, we just set x squared minus 1 equals 0. A couple ways to work it. You could notice that it is difference of squares, and then you set each of the factors equal to 0, and you get x equals 1, negative 1, and x equals positive 1. You could also, in this case, add 1 to both sides, and then take the square root of both sides. And when you do, you get plus or minus 1 that way as well. So that means that x is all real numbers except negative 1 and positive 1. We can also say it's negative infinity to negative 1, union with negative 1 to 1, union with 1 to infinity. But that should be a review. So your turn to try it. Try to find the domain of this function. Okay, so hopefully you paused the video and you found the domain. So we're going to set the denominator equal to 0. And what's nice about this one is that it's already factored. So we can just take each of the factors and set them equal to 0. So the 5 we don't really have to worry about because 5 can't equal 0. So we just set x minus 1 equals 0, x minus 5 equals 0. You get x equals positive 1, x equals positive 5. So all real numbers except x equals 1 and x equals 5. If we were writing it in interval notation, it would be negative infinity to 1, union with 1 to 5, union with 1 to infinity. Alright, so let's identify vertical asymptotes. So to identify vertical asymptotes, it's kind of similar to how we start off with finding the domain. First, you're going to factor the numerator and the denominator and note any restrictions in the domain of the function. Then you're going to reduce the expression by canceling common factors in the numerator and the denominator. Okay, so you have to make sure you do that. Make sure that if there's anything common in the numerator with anything in the denominator, once it's been factored, that you cancel it out and make note of it. Note any values that cause the denominator to be 0 if in the simplified version. These are where the vertical asymptotes occur. So you must simplify it first before you find the asymptotes. And note any restrictions in the domain where the asymptotes do not occur. These are removable discontinuities or holes. So let me just show you. So this graph here is the same as this one. We just didn't have enough space there. Okay, so it says identify the vertical asymptotes. So what you're going to do is you are going to rewrite this in factored form, the numerator and the denominator. So in the denominator, the factors of negative 36 that add up to be 5 are positive 9 and negative 4. So this has been factored. I can't cancel anything out, so there are no holes. Okay, so up here it says that if we cancel anything out, any restrictions in the domain where the asymptotes do not occur, these are removable discontinuities or holes. And so you can see that if we have x plus 9 and we set that equal to 0, and x minus 4, we set that equal to 0. Now the reason we do that is if you set the denominator equal to 0, then you would set each factor equal to 0, and you would get negative 9 and positive 4. Now this corresponds to what the domain is. The domain is all numbers except for, all real numbers except for negative 9 and positive 4. So if you look at this graph, Look what happens at -9. The graph approaches it, but it doesn't cross it. Look what happens at 4, and it looks like these are 2, 4, 6, 8, 10. They're counting by 2, so 4 is about right here. The graph approaches again, but it doesn't cross it. So that's what's going on at the vertical asymptotes. Okay, so let's talk about removable discontinuities. A removable discontinuity occurs in the graph of a rational function at x equals a if a is a 0 for a factor in the denominator that is common with a factor in the numerator. So if we were to factor the top and bottom, and if there was a factor in the bottom that canceled with a factor in the top, then that means you wouldn't find a vertical asymptote with that factor. You would find a removable discontinuity instead, which is basically a hole in the graph. Now, there is a small exception to that. This is true if the multiplicity of the factor is greater than or equal to that in the denominator. If the multiplicity of this factor is greater in the denominator, then there is still an asymptote at that value. So what that means is, if it's a greater multiplicity in the bottom, that means that factor is not going to cancel completely out. So if it doesn't cancel completely out, then it will still be a vertical asymptote. Let me show you what I'm talking about here. You need to find the vertical asymptote and the removable discontinuities of this graph. So the first thing that you would need to do is factor the top and bottom. The top doesn't factor, but the bottom is difference of squares, then factors into x plus 5, x minus 5. Now, when you're finding vertical asymptotes, you set the denominator equal to 0, but before you can do that, you need to make sure you've simplified this. So if we simplify it, the x plus 5's cancel, and that leaves 1 over x minus 5. So that means the vertical asymptote, we take the x minus 5 equals 0, and we solve it, and we have a vertical asymptote at x equals 5. However, there is a hole in the graph, or a removable discontinuity, at x plus 5. So if we solve this one, we see there's a hole in the graph at x equals -5. Because here's the deal. If you were finding the domain, you would use this denominator, and it would show you that x is all real numbers except for 5 and -5. And at 5, there's going to be a vertical asymptote. Well, at -5, there's not a vertical asymptote, but it's still a hole in the graph because that value would still make the function undefined. Okay, so that's all for part 1. We'll pick up with part 2 in the next video.